Hi class, we continue our study in chapter 4 by moving into the final section of chapter 4, and that's section 4.6, talking about isosceles, equilateral, and right triangle. So we have two objectives in this section. First one is we want to use properties of isosceles and equilateral triangles, and then the second thing we want to do is use properties of right triangles. And we'll actually end the lecture doing a proof involving right triangles. All right, so just to recall in section 4.1, what we did was we classified triangles by their sides. Okay, so we learned that a triangle with at least two equal sides, so two of the sides of the triangle are congruent or equal, that's called an isosceles triangle. And a triangle with three equal sides is what we call an equilateral triangle. All right, so some definitions. If there's an isosceles triangle, all right, has exactly two congruent equal measure sides, then these two sides are what we call the legs. So if you here on this triangle here, what we're saying is these two sides are congruent. These are classified then as legs of a triangle. The third side here in the blue is what we call the base. And the angle opposite the base is what we call the vertex angle. Right? These other two angles here, so the other two angles adjacent to the base, right? These are what we call base angles. Right? So these two congruent sides of the legs, opposite that is the base. The angle opposite the base is called the vertex angle, and the angles adjacent to the base are called the base angles. All right, so a couple theorems. So this first is called the isosceles base angles theorem. So if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So if we have that side AB is congruent to side AC, then it must be that angle B is congruent or has the same measure as angle C. All right, so let's work a problem. So use the figure and markings to find the values of x and y here. All right, so first off, we notice here that this is 58 degrees. These two sides are congruent. All right, so going back, all right, looking here, these are the legs of the triangle. All right, if these two sides are congruent, then the angles opposite those two sides, so angles x and y, then they must also be congruent. So triangle ABC is an isosceles triangle. So the base angles here are equal in measure. So the measure of angle C is equivalent to the measure of angle B, or x is the same as y. Finally, using the sum of the measures of the angles of a triangle, well, we know that the interior angles all must sum to 180 degrees, right? Otherwise, it wouldn't be a triangle. So simply, we have to have 58 plus x plus y is equal to 180. Let's subtract the 58 over first. Well, now we have x plus y is equal to 122. Well, what we know, if we look back, was that y was the same thing as x, so we can have x replacing y with x. We have x plus x is equal to 122, or 2x is equal to 122. Finally, dividing by 2, we just see that angle x is 61 degrees. What that also means, right, since x is equal to 61, right, and we know that x and y are the same, then y is also equal to 61 as well. All right, so if you check this, if you add 58 plus 61 plus 61, it does indeed add up to 180 degrees, so this worked out, it's fine. Another one, right, this is the perpendicular bisector theorem. All right, so the perpendicular bisector of the base of an isosceles triangle. So if a line bisects the vertex angle, right, like here, right, the vertex angle, remember, is the angle opposite the base, right, then the line is also the perpendicular bisector of the base. Right, so what that means, another thing, if side AB is congruent to side AC, right, and this is an angle bisector, so that angle 1 is congruent to angle 2, then what we do know here is that this right here, this AD is perpendicular to BC, and as a result, these two sides, BD, is the same thing or congruent to DC. All right, let's work a problem involving this perpendicular bisector of the base of an isosceles triangle theorem. So you're given this figure, all right, and what you want to do is you want to find the value of this angle x right here. All right, so since segment AB is congruent to segment AC, we see that right here, and we're also being told that this angle is congruent to this angle, Then by the isosceles base theorem, angle A is congruent to angle C. So we know that this angle here is 51 degrees. From the markings on the triangle, right, we see that segment BD bisects this angle right here, ABC. So by the theorem, we know that BD here is perpendicular to AC, right? So what that means is then that angle BDC is 90 degrees. So think about what we've just said here, right? This is a 90-degree angle. This is 51 degrees. We're looking for this right here. Well, it must be then that the measure of angle C plus the measure of angle BDC, this one right here, and the measure of angle DBC, X, which we're looking for, must be 180 degrees. So simply 51 plus 90 plus X is 180 degrees. So adding these up and subtracting from 180, you just get angle X is equal to 39 degrees, right? And that's what we're seeing right here by using that theorem. All right, let's do another one. So a corollary from this. If the triangle is equilateral, right, then we have the equilateral triangle, and this is a corollary to theorem 4.6-1. And here's the corollary. If a triangle is equilateral, then the triangle is equiangular. So excuse me, if the triangle is equilateral, then it's an equiangular triangle. So if the sides are congruent, so side AB is congruent to BC, congruent to CA, then all the angles must be the same. So angle A must equal angle B must equal angle C right here. So another corollary from this, if a triangle is equiangular, then the triangle is equilateral. So meaning if I tell you that all the interior angles are the same measure, they're congruent, then all sides must be congruent as well. So it works both ways. All right, let's do another problem. Each triangle in the floor pattern shown here, all right, is an equilateral triangle. So I'm telling you there that all the angles, or excuse me, all the sides are congruent, so they're all the same length. So find the measure of each angle in this triangle, X, Y, Z over here. So let's want to find the measure of all these angles here. All right, since this triangle XYZ is equilateral, then it is also equiangular. So we have a triangle with three angles of equal measure. So I'm telling you then it must be that the measure of angle X is equal to the measure of angle Y is equal to the measure of angle Z. So it must be that all these angles sum up to 180 degrees. Well, since they're all equal, I'm just going to replace the measure of angle Y with the measure of angle X because they're equal, and the measure of angle Z with the measure of angle X because they're equal. So 3 times the measure of angle X is 180 degrees. Dividing by 3, the measure of angle X then just has to be 60 degrees. And all these angles here, measure of angle X, measure of angle Y, measure of angle Z, are all 60 degrees. All right, final theorem for today. All right, so theorem 4.6-6. This is called the hypotenuse leg or HL theorem. And it goes like this. If the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of another right triangle, then what we're saying here is the triangles are then congruent. So if you can somehow prove, all right, that two different triangles, triangle PQR and triangle XYZ are right triangles, their hypotenuses here, all right, are both congruent, and then any leg of the triangle is congruent with the same corresponding leg over here. So right angle, leg, hypotenuse, right? Then you must be, there's no way you cannot have this. Triangle PQR is congruent to triangle XYZ. All right, so to use the hypotenuse leg theorem, the triangles must meet 3 conditions, right? There are 2 right triangles, right? So they both have a 90-degree angle. The triangles have congruent hypotenuses, so, the side opposite the 90-degree angles are congruent. And there is at least one pair of congruent legs. All right, so let's do this. I want to prove 2 triangles congruent using the hypotenuse leg theorem. So segment BE right here bisects segment AD at C. So it bisects it at C right here. All right, so that tells you that this cuts it in half. All right. We know that side AB here, all right, is perpendicular to side BC, and the same thing over here. DE is perpendicular to EC. And then finally, we know that AB is congruent to DE. All right, and what we want to do here is we want to prove that triangle ABC is congruent to triangle DEC. All right, so what you can see here is you're ultimately going to want to use the hypotenuse-leg theorem. Right? I've got an angle here. They're congruent. They're 90-degree angles, and I've got one leg of the hypotenuse here. Right? So you might be thinking, well, I could do angle or side angle side. You could do that, but what I want to do here is I want to use this hypotenuse-leg theorem. So what I ultimately need to do is I need to prove that segment AC, right, is congruent to segment CD. That's where we're going to be going. And then once I do that, I'll be able to use the hypotenuse leg because I got congruent 90-degree angles, congruent legs, and then congruent hypotenuses. All right, so here what we do to use the hypotenuse leg theorem, make sure you note that the two triangles are right triangles in your proof. All right, so let's go through the statements. Side BE bisects AD at side C. That was given. All right, so BE, let me go back, sorry. BE bisects side AD at C. All right, so it cuts this AD at C right here. It must then be that AC is congruent to side CD. So we're able to say this side here, AC, is congruent to side AD here. Right, and that's by the definition of a bisector because it cuts it right down the midpoint. We were also given here that side AB is perpendicular to BC, side BC, and side DE is perpendicular to side EC. That was given. So what we're able to then say, because they're perpendicular, that angle B and angle E are right angles. Right, that's the definition of a perpendicular. Right, so what we're able to say then is triangle ABC and triangle DEC are right triangles. That's important to note. Okay, that's the definition of a right angle. Then what we're able to say is side AB is equal to side DE. Right, that was given. So I've got one leg is given. I've got the hypotenuse, or the two legs are congruent. That was given. I've got the hypotenuses are congruent. That was given. And then I've got that they're both right angles. So I'm able to say then that triangle ABC is congruent to triangle DEC. This is by the hypotenuse leg theorem. So a little bit different than how we were doing like side angle side or angle side stuff. But you can also approach proving two triangles congruent this way as well.